SFEPY has some grading capabilities, but and they are really good. They're good for most problems, but if you want something very, very complex, then there are other packages better for that, better suited for that. So let me see some other examples here. For example, this package is a grading package. You can use look at this kind of problems, right? Oh, we should try to solve maybe to find a here. Okay. Yeah, look at this. There is a Navier-Stokes term. I don't know, for some reason it didn't show up in the. Well, that's the term. So let me see other problems they have used for. He has used the problem for. So the good thing is that there are many different examples, and there are examples for linear elasticity, and examples for multiphysics, and Biot, for example, poroelasticity is one of them. It can work in parallel. You can solve the kind of equations, and you can solve it in parallel. They use PETSI, and MPI is very advanced. So if you know what I'm, they have meshing capabilities as well. So the bottom line here, and what I want to let you know, is that doing this kind of is there a question? Doing this kind of calculations, the software that you need for doing this kind of calculations is typically very expensive, and one of the reasons probably we haven't seen too much growth into many of these applications in petroleum is because the software is expensive and not very available to many people. But now we have the ability to use this, and this is just one of them. This is my favorite one, let's say. But there are many other packages for finite elements in Python, which are open source. No, I forgot what I was doing. Examples. In
the comments, I sent you a gallery.
Oh, okay.
That has more visual. At the top in the messages, just next to the participants icon. No, you were there.
Okay.
Just at the top of the icons. Go to the top of the icons with microphone. Then next to the yes, over there.
Okay. Yeah. Well. Yeah. So let me see if there is Navier-Stokes here. Well, for example, this kind of problem can be used for wallboard stability, or it is acoustic, so yeah. So it will be interesting if you have ideas and something that I have my own applications that I have worked in the past, but certainly it would be interesting to see if you have any of you have an interesting application that we can work. Yeah, I don't see the Navier-Stokes here. Because equation. Oh, there's more. Oh, Navier-Stokes. Okay, here it is. Well, this is interesting. Oh, well, there's something else. You can use this package as a black box solver. And then you can specify things in different ways. So I don't like this way. They have two ways. They have this, I don't remember how they call it, and they have the interactive way. The interactive way is what I showed. But you can do it this way too, where you basically specify things as dictionaries. So for example, options, you define them here as a dictionary. Then look at the regions. So and then materials and so on and so forth. I prefer the interactive way. But this is also available, and not too many of the examples are interactive. Well, look at this. This is a BIOT problem. So this is a copper flow mechanics problem. I have an issue with these equations. I don't think they are correct, but I use this example for one of my papers. So this is what you can do. You have an idea for a paper. You can come here and see what kind of problems you are trying to solve, and start from there. So much better than starting from scratch. Right? Starting from scratch is going to take you years to solve one of these problems, and it's going to be just that problem. So yeah, well, that's what I have today. So hopefully we can build from this and start applying it to interesting problems in the next sessions. I don't know. Do you have any other question? I guess not.
Well, to me, it was very good. It was enlightening. So thank you.
Yeah. Okay. Welcome. I mean, I know that looking at something new may be challenging, but we have to start somewhere. Right? So what I'm showing you is that this solving problems that you saw on the gallery or the one I showed will be very, very difficult if you had to write the code yourself. So there are no limits here.
So when you open the VTK file in ParaView, it's because where did you export the file?
Yeah.
I didn't quite get.
Let me see. I'm not seeing my notebook. Did I close a note?
In the second. Yeah.
Let me open it again. I don't know why I don't see it. This is my issue with the notebooks. I always get lost with them. It's not there. It's not here. I may have closed
maximize. Just maximize. Right click and maximize. The one that you want to. No, not that one. On the icon on the Chrome icon. Yeah, there is one of those that is hidden. I think it's a second. Oh no. Yeah, exactly. The middle one. You probably need to right click and maximize. Yeah, right click on the middle.
Yeah, it's because it's going to the left. That one doesn't have it. I don't remember having closed it, but it's not there. Wow, that's weird. That's weird.
It crashed.
It probably crashed. Let me open it again. It's not going to take too much. And the funny thing is that here it's still running. It's supposed to be running. Anyway.
And you only set up one-time step here.
Yeah, it's because it's a static problem. It's not a time-dependent problem. You see, time is not it's not in the equations. So yeah, let me show. here. No, not there. Once you have your problem solved, PB is the problem, right? And then you say save state, and then you provide a name and whatever you want to solve. Back is the place where I store the equations, the solution to the equations. So you see PB is my problem, right? I define my problem here once I had all the boundary conditions and everything. And then you have the vector with all the solutions. And then PB save state here. You see I'm providing this name. And then I go to paraview, and then I have that linear state, linear elasticity. Yeah. So you always need to save it, even if you use the internal viewer, because you specify the file, your result.
And in paraview you cannot see the deformation.
No, because this is the issue with mechanical problems. The solution of a mechanical problem is the deformation. So, and it's typically represented with a color or something in normal views. But here they created this function within SFEPY to provide that ability, which for mechanical deformation problems is much more useful. It's very useful because you can have a more intuitive understanding of what's going on. So that's really, if you wanted to visualize something like that in paraview, you need to write your own. You need to apply the deformation to each node. So move each node accordingly, and then you go and visualize that. So, but the problem is you don't know exactly what the scale that you need to apply is, because the deformations are usually very small. If you apply them without the scaling, then you are not going to see much. So this is a very powerful feature here.
For a problem where you want to see, for instance, whether a material could fail, let's say a pipeline, and could fail due to exceeding a threshold of stresses. Yeah. What is it that you would expect to see on the viewer, and how you would identify the failure of a material? Yeah,
that's a good question, right? Because typically you have a constitutive equation that contains the way the materials deforms. Linear elasticity is just one of them, one of the constitutive equations, and it doesn't contain any failure. But what typically we do is that we identify a particular threshold of properties, which is defined by a Moore Coulomb or some other failure criteria. It's some kind of surface. So if your shear stresses exceed some magnitude compared to the normal stresses, for example, then you can have failure. But so you can solve your elasticity problem, your problem with linear elasticity, which is simple to solve, and then you evaluate some kind of failure envelope. The envelope is a right criteria, and if you are within that envelope, you are okay. If you're outside that envelope, then you may have a problem. So that's one way to do it, because otherwise you need to solve a nonlinear problem, which may be really, really complex to solve. The way, for example, in Weilbrodt stability problems, the way it's done is typically the way I just described. So you have some kind of envelope, and then you're solving your problem, and once your points start getting outside, of the envelope, then you identify those points as bad points. And the reason for solving the linear problem, the justification, is because you don't care what happens after failure, because what you want is to avoid failure. So you are solving a problem to find the conditions such that you don't have a failure. And after failure, you really don't care, because it's a completely different problem, right? So,
yeah, unless you want to induce a failure.
Unless you want to induce a failure, like in fracturing or something like that, right? So yeah, each problem have its own characteristics, and the thing is that you always want to solve the easiest, the simplest problem, right? So typically for Weber stability, the idea is to you want to identify a mod weight or things like that that keep you within the envelope, and then you always solve a linear problem such that you are within that envelope. If you are solving, but sometimes you cannot avoid solving the nonlinear problem, right? So and that's because once things are in the nonlinear region and you want to keep predicting what's happening, then the only way to do it is by solving the problem. But yeah, that's one of the interesting questions, especially because failure is certainly one of the things that we need to investigate more often within these problems. So,
Thank you.
Okay. Hopefully you enjoy it. So, and hopefully we will have some ideas. I have my own applications that we can work, but certainly will be much more interesting if we investigate the problem that is suggested by the community, by somebody in the community. Great. Okay, let me know if you have questions. We will have more sessions on this. So if you really found interesting.
Yeah, Adolfo, just have one other question.
Yes.
You said that we are going to have a second part of this topic of finite elements.
Yes.
So, I just want to know what kind of tool do you recommend for this part of the meshing?
Okay.
Previous to the finite elements, do you have some Python package for that, or which is the one that you use?
Yeah, well, I use Gmesh, which is GMSH, I think, and
but it's open source.
It's open source, yeah. Okay. There are many. GMSH. I call it Gmesh. Let me copy this is my favorite one, but there may be others. There are many, and this is not Python. This is not, but it has a graphical user interface. And there is somebody wrote Python bindings, so you can use Python to generate the meshes. Yeah, but this is open source and you can use it with. But also SFEPY itself has meshing capabilities. The question is, I used this package several years ago, and I was really very experienced with it. And now I decided to have this session. And when I checked the package, it had changed a lot, so it's much better now. So I think I'm gonna be investigating a little bit more, so I can recommend something. But let me know what kind of meshes. You can send me an email or something. What kind of mesh you are trying to generate? Are you trying to generate something very complicated, or?
Oh, not really. I made finite elements and a FEM analysis a couple years ago, but the mesh was not very complicated. But I'm just trying to get deeper into this topic of the finite element analysis. And I have read a little bit that there are some rules, some key aspects that you have to follow previous to do the mesh and some other things. Yeah. Because the structure that I did, it was very simple. It's just a pipeline, and I have to do the tuning just in the edges, but not really a very complicated structure.
Yeah. Yeah, this meshing packages typically they have verification and correction criteria for your mesh. There's also this one that mesh that gen I mean that gen. Also, it's not Python, but there are other things that are written in Python. But you can generate any kind. If you look at the galleries there, or I can show it here. Look at the kind of things they do. They use it for. So you can really use it for anything that you want. And this is Gmail. So it's
cool.
it's and you know they are not difficult to use depending on how complicated is your application. But Gmail has this full graphical user interface.
Wow.
So you can
you can use it for reservoir modeling, for example.
Well, you mean like for reservoir simulation?
Yeah, for reservoir simulation.
Yeah, no, because these are finite element meshes. For reservoir simulation, you need finite volume or other kind of meshes. Because these meshes are node. You need connectivity and nodes, right? And reservoir simulators don't use those kind of meshes just because they're finite volumes. I guess I'm not sure if intersect.
That is what people call finite volumes or something like that.
Yeah, finite volumes. Okay. Yeah, because finite volumes, you basically what you need is but depending on the mesh, right? If you have corner point, but let's assume you have Cartesian grids. You have something like NX and Y and Z, right? And then you have volumes. So it's much simpler than the geometries that you can apply for. You cannot express very complicated geometries using finite volumes. It's not possible.
Very interesting.
Yeah. Your finite element, and also
okay,
for you.
Okay, thank you so much, Alejandro.
Yeah. Welcome.
Sorry. Thank you so much. Problem.
Okay, let me know. We can always chat and send me messages if you have some more questions. All right. Thank you very much, guys.
Sure. Thank you.
All right. Have a good